In this example, we have a function y equals f of t that represents the number of miles that we've driven from home after t hours. And the first question is just asking, what are the units? What are the units of f prime of t? Well, first of all, we know that f prime of t, that's the derivative um, of the function, and the derivative is essentially the average rate of change of the function over a very small interval. So I can write it as the change in y over the change in x, right? For a small, actually not x though, because it's t, right? So let me write t, delta y over delta t for a small delta t. Okay, now to find the units of the derivative, we can look then at the ratio of this fraction, right? This delta y over delta t, right? So the units are going to be in miles, right? Because the numerator is miles. It's the change in the number of miles that we've driven. And the denominator is just the change in time, and time is in hours. So the units of the denominator are hours. All right. So the units of the derivative are in miles per hour. Now we could write that as miles per hour. Okay, we could write it that way. Sometimes it's written as mph, or we can actually just write miles. We can abbreviate miles as mi. You have to abbreviate it as mi because m is meters typically, and then h is hours, or you could write hr for hours. Okay, so but the key here is that Leibniz notation allows you to see that the derivative of a function is the change in the y for a small change in t, and so the units of the derivative are just the units of the numerator, which is the as the dependent variable, right? And over the units of the denominator, which is the the independent variable. Okay, right? Dependence on top, independence on the bottom. So the units are miles per hour. So that helps us interpret what the statement is saying here. F prime of 2 is equal to 65, right? So what does this 2 represent? The input to the function was t, so the input to the derivative is also t. T is an hour. So this means 2 hours. And this 65 represents the rate of change, right? It's the rate of change because our function was for distance. It's the rate of change of the distance over time, all right? So this means 65 miles per hour. I'll just abbreviate it mph. This means 65 miles per hour. Okay, now, so the derivative is the rate of change of the dependent variable as we change the independent variable. And so, but we have a special name for this rate of change of distance over time, right? It's called velocity. So what I can write is that at 2 hours, right? So after we've driven for 2 hours, this is telling us our rate of change, right? It's telling us our velocity. So our velocity is 65 miles per hour. 65 miles per hour. Okay, that's our interpretation of this statement here. This is a mathematical statement, and then we have the statement in plain English here. All right. So, to summarize that, we're talking about the key idea here is what the units of the derivative are. And so if we have a derivative, dy by dx, the units of the derivative are the units of y over the units of x. So it's the units of the dependent variable over the units of the independent variable. And sometimes we read that as, the units of y per the units of x. Now, if the derivative is not changing rapidly near a point, then we can also interpret this, the derivative, as being approximately equal to the change in the function when the independent variable increases by 1 unit, right? Because it's, like in our example before, our units were in miles per hour. So if we're not changing that miles per hour very much, that's saying we were going 65 miles per hour would mean that over the course of 1 hour, we would cover 65 miles. Our change in distance would be 65 miles. But that's if our derivative is not changing rapidly. But that's a good approximation, is that if we continue to drive at 65 miles per hour, then our change in distance would be 65 miles for a change in 1 hour. Okay? All right, I'll see you in another video for the next example.